we are finally ready to implement the function that initializes a neural network. And in order to do that, we are going to open the editor window in a function named init network. And then let's say that omega is the shape of the network. So that's going to be the right argument. And let's just say that it's going to return a pair of weight matrices and bias vectors. What this means is I'm going to create or to generate the weight matrices and the bias vectors separately, and I'm going to keep them separately. And that's just the format I chose for this neural network. You could try with different formats, and well, let me know how it goes. It's just the particular formats we chose. And then the shape of the network refers to, if you'll allow me to open the sketch I have, the shape of the network refers to the number of neurons there is in each layer. So for this example network, it's 362. And so in our example, the shape is 362. Let's type it here because we're going to experiment with it. And while implementing this function is really, really easy, the first element of the pair is going to be the weight matrices with the shape omega, and the second element is going to be the init of the bias vectors of the shape. So we are basically just deferring the work of this function to two different functions, the init weight matrices and init bias vectors. So let's go ahead and see what this function should do. So we are taking the shape of the matrix, our 362, and we need bias vectors for which layers. If you check the sketch, if you check the sketch over here, you can see that we need a bias vector here and a bias vector here, but we don't need one in the first layer. So we can actually drop these first three and then create a normal vector of shape 6 and a normal vector of shape 2, and afterwards make them column vectors. So that's basically just it. We drop the first element of the shape, and then we are going to make a normal array with each one of those numbers. So you can see here I have a vector of size 6 and a vector of size 2, and then afterwards we just want to turn these into column vectors with the table function. And we can do this by using the bind operator, the beside operator, to do the table after the make normal array. So that's it. That's the init bias vector. So we can go ahead and store it in our function. Let's create a diff, and let's say that omega is the shape of the array, the network, and then it returns a vector, returns a vector of bias vectors, exactly, vectors. And then we saw that it's just the table after making the normal array of each one of all the numbers in shape except the first one. And actually I lied. I'm sorry, I didn't mean to. There's just something else we need to do, and it's just something, it's more important than it might look at first glance, and it's better that we do it just now. These numbers are too big. Okay, so when we create an actual network that we want to teach something, and in particular for the example we're going to use, it's much better if the numbers, if these initial random numbers are smaller. And it has to do with numerical stability and like the way the calculations can explode or behave badly if the numbers are too big. And there's research papers that explain exactly what this is and how to avoid it. And a quick and dirty way of avoiding it is taking each vector and dividing it by the square root of the number, by the square root of the amount of numbers it has. So in here we divide each number by the square root of 6, and in here we divide each number by the square root of 2. and this will create smaller vectors. And it's because APL is a array-oriented programming language, this is fairly easy to achieve. We can just save the dropped shape, so the numbers we actually care about. So we can do is we take the shape, so this is the exact same thing we have, but then we are going to take the square root of the shape, or better, the square root of each element of the shape, and then we divide it switch by the things we got. So this creates the vectors, the column vectors we have in here, and then we are dividing each one by the square root of the corresponding number in the shape. So if you go ahead and press escape to fix this function, init bias vectors, we can give it the 362, let me write it explicitly so there's no confusion. And you can see it generates a column vector with 6 numbers and with 2 numbers, and these are overall smaller. Of course this is random, and it's hard to see that it's actually creating random numbers, smaller random numbers, but overall it is. You can see that empirically I haven't seen a single one in here, and over here you have a number that was almost 2, 1.5, so yeah. So that's the bias vectors. And for the weight matrices we need to do something similar. So this is the shape of the network. What we need to do is, and I'll open the sketch of the network right here. For each of the, okay, so this is the shape. And for this pair of numbers right here, I need to create a matrix with this shape. I even made the drawing in a previous video. We need to have a matrix with 6 rows, which is the number on the right, and 3 columns, which is the number on the left. So what we actually want to do is create pairs of consecutive numbers with comma reduce, but switched, so they get put in the correct position. So if you recall, 2 comma reduce shape is going to create pairs of consecutive numbers, but I want these to be switched so that they're suitable to use as the shape for the matrices. And then I just have to apply the make normal array to each one of those. Sorry, it's much faster if I just do this, yes. I'm going to apply the make normal array to each one of those. And then again, we will have to divide by the square root of the total amount of numbers each matrix has. And so the total amount of numbers each matrix has can be obtained by multiplying pairs of consecutive digits. And so we just have to take these matrices and divide by this. That's how it works. So if I close this and maximize this window and give this enough room, we can go ahead and open the editor window for the init weight matrices function. Let's go ahead and make a diff out of it, and let's say that omega is the shape of the network. Let's say that it returns a vector of weight matrices. And let's just do what I said. Well, the matrices are the make normal array of each one of the switched consecutive pairs of numbers. And then in the end I just have to divide each matrix by the corresponding products. So omega here, so this is creating pairs of consecutive digits, but I want the square root of it, so I'm raising it to the power of 0.5 switched, and then dividing everything. Now if I press escape, and then also press escape in here so that this init network function is fixed, I can go ahead and initialize network with shape 362, and you can see here I'm getting, so there's 2 larger boxes. The second one starts here, and this second box has the bias vectors in here, and then the first box that goes all the way up here has the 2 matrices. And in general, the way we are going to use this function is by typing something like open parens, WB, close parens, and then the assignment. And this basically just unpacks the results. This gives me the weight matrices, and this B gives me the bias vectors. And so we can just use both of them separately, which is going to turn out to be quite helpful. And there you have it. You have a function that initializes a network that is ready to learn. So next step, teaching the network how to take input and produce some output.